Guys, in this video we are going to see an example of cascaded op amplifiers. In this particular problem we have asked to find out this Vout voltage. Okay, now when we deal with op amplifiers we have to know two things. Whatever the current entering or exiting this positive and negative terminal is always going to be zero. Okay, and also we have to know that voltage across this positive terminal is going to be equivalent to voltage across the negative terminal. So if we call this one V1 plus, and if we call this one V1 minus, V1 plus is going to be equivalent to V1 minus. Now using this two information, let's see what we can figure it out first. So if you look at this bottom part right here, these two are connected to the ground. So this is zero voltage, this is zero voltage, and we have 5 ohm resistor, 6 ohm resistor, and also we have a voltage source. Now using this one we can find out this V1 plus, because you can see this is a voltage division, and if we use that one for this bottom part, V1 plus is going to be equivalent to this voltage source multiplied by 5 divided by addition of these two resistance. That's going to be 11, right? And that's going to be our V1 plus. And if V1 plus is this value, then from this information we know that whatever the voltage across the negative positive terminal is going to be equivalent to negative terminal. So we can say V1 minus also going to be the same thing. Okay, now let's see what we can find from this information. Here if you notice, here we have a voltage source and this node is right here, and we know that current entering this op amplifier is going to be zero, right? Current entering or exiting, that's going to be 0 ampere, so there's no current entering or exiting. So this, if we call this current Ix and this is Iy, this Ix must be equivalent to Iy because there's no current going through anywhere else, right? So we can say we are applying Kirchhoff's current law at this point. Okay, let's call this one KCL at V1 minus. Okay, so this is V1 minus, and this current must be equal to this current, so we can say Ix is equal to Iy, and current is equal to voltage over resistance, and here the voltage is going to be VA minus this voltage. We found out this voltage, so VA minus this voltage is VB 5 VB by 11, right? 5 VB by 11, that's going to be equivalent to Iy. Iy is going to be this voltage minus Vx, and this voltage is the same thing, that's 5 VB over 11 minus Vx. Okay, and also we have to divide by the resistance, right? Voltage over resistance, so the resistance in between is 3 and in the other one we have 4. Okay, now let's try to simplify this one. Now to get rid of these denominators we can multiply both sides by 12. If we multiply this one by 12, we are going to get 4 times VA minus 5 VB over 11. In the other one we are going to have 3 times 5 VB over 11 minus Vx. Let's multiply this one. This is going to be 4VA minus 20 VB divided by 11 is equal to 3 times 5, that's going to be 15 VB over 11 minus 3 Vx. Okay, and this is what we are getting right now. Now also we can get rid of this 11, right? If we multiply both sides by 11 we can get rid of this 11 also. So let's get rid of this 11. So if we multiply by 11, this is going to become 44 VA minus 20 VB, and in the other side we are going to have 15 VB, and this is going to be just 33 Vx. Okay, here we are interested in finding Vx, because if we find Vx, that's going to be the voltage across this positive terminal, because we don't have any current or anything like that here. So this is going to be, if we find this voltage, this is going to be exactly same at this point, and if we find this one, that's going to be equivalent to here. So that's going to help us to find this Vout, right? So we can solve for Vx. Let's rearrange this equation. So here if we bring this Vx to this side and bring the others to this other side, this is going to become, okay, let's bring this 15 VB to this side So this is going to become 44 VA, and here we are going to have negative 15, negative 20, that's going to be negative 35 VB, and that's going to be equivalent to negative 33 Vx. Therefore Vx is going to be equivalent to 4 VA minus 35 VB over negative 33, or we can just switch the sign. If we switch the sign, it's going to be 35 VB minus 4 VA divided by 33. Okay, if you wonder how did we get positive, because I substitute this negative. If you multiply both sides by negative, you will get the opposite like this, right? So that's how we got this one. Now we have the Vx value. Now the next thing is we are going to solve, our purpose is to find V out. Now we have Vx value, and this Vx value is going to be equivalent in the both side, because V2 plus is equal to this one Vx, this is equal to Vx, then V2 minus also same thing, because we know that for an op amplifier the voltage across the negative terminal is equal to voltage across the positive terminal, and we know the positive terminal voltage, and that's going to be voltage across the negative terminal. Okay, so we have this voltage, and this is going to be the voltage across here, and we know that again we can use the Kirchhoff's current law, and let's assume, you can assume any direction for current, like let's say the current for this one, let's call this one IW. Let's say IW is going in this direction, and let's say IZ is going in this direction, and from this one we can create a Kirchhoff's current law. Kirchhoff's current law says whatever the current entering through the node should be equal to current exiting through the node, or addition of all the current in the node should be equal to 0. So in this one we can say addition of all the current in the loop is, in the node is equal to 0. So if we add these two together, IZ and IW, that must be equal to 0. IW is equal to 0, and we know that for a op amplifier, current through this one and this one is always going to be 0. So there's no current flowing through this op amplifier. So IZ plus IW is equal to 0, and IZ is going to be this voltage. Okay, here we have Vx minus 0, because this is connected to the ground. So Vx minus 0 divided by 1 is going to be IW. Okay, let's write this one in terms of voltage and resistance. So here we are going to have Vx minus 0 divided by 1, and that's going to be equivalent to negative of this one, or we can just add them together, right? Like plus, and this is Vx and this is V out. So Vx minus V out divided by the resistance in between, that's 2, is equal to 0. Now to get rid of this denominator, we can multiply everything by 2, and if we do that, that's going to give us, this is going to become 2Vx. Here we are going to have plus Vx minus V0. I can move this minus V0 to this side, that way we will get V0 right here. Therefore V0 is, let's say VO, right? V out is equal to 3Vx. So this is equal to 3Vx. Therefore we know the Vx already, right? We found our Vx right here. Now let's get rid of this part, because our final answer needs some space. Let's get rid of this part. Okay, let's continue here. Okay, so V out is equal to 3Vx, and we found out Vx is equal to this one, right? So we have to multiply that one with 3. 35 VB minus 4VA divided by 33, and 33 and 3 cancels, and this is going to become 11. So we are going to get, I think I made a mistake right here. Let's see. So this one is 4V. This one is 44 VA, right? 44 VA. Okay, so here we are going to have 44 VA right here. 44 VA divided by 11. So the final answer is going to be 35 VB minus 44 VA divided by 11. and that's going to be our V out. And that's how we do this kind of problems. I hope this helps. Thanks for watching.